Okay, off we go. So here's where we left off last time. We were just about to start section 7.3. So I said some introductory things, very, very broad, about how what we're going to be doing in this section is going to be sort of a three-dimensional version of the accumulation theorems that we saw in chapter 6, right? So it's kind of a revisit in a way. And there's differences, of course. These are three-dimensional instead of two, right? That's a big difference. For example, there are just different geometry to be dealt with. So, of course, there's going to be a lot of differences, but there's going to be a lot, and that's going to be the same. So, you're going to notice as we go through this, just as a reminder, I already said this last time, that the structure of the approach that we're going to be taking here is going to be a lot like the structure of the approach we took for Green's theorem. And this is all on purpose. I'm trying to emphasize as much as possible how these theorems are all really very, very much alike. After all, they're all special cases of the same generalized theorem. So they're literally the same theorem, just showing up in different contexts. So, okay, so just a reminder. As with this chapter 6 theorems, we're going to talk about boundaries and what the orientation means on boundaries. Whoa, I hit the wrong button there. We are going to talk about an accumulating quantity. And we're going to establish that it is, in fact, an accumulating quantity. We're going to be reminded pretty quickly that accumulating quantities have this feature that you can think of them as happening in the interior, even if they're computed on the boundary. And as such, they behave like stuff. Whatever stuff you want to visualize as being kind of like, I like mass. It's the most relatable kind of stuff. And as such, being as it is kind of like stuff, we can talk about its associated density. So, and then with all that put together, and a quick interpretation that results, we're going to have ourselves a theorem. So now this is the exact same structure and strategy that we went through to establish Green's theorem. So please keep all that in mind as we go through these ideas now in slightly more detail. I am not going to be as thorough with this as we were for Green's theorem, because this is not our first time, right? And you're going to be noticing, it's just like it's kind of the same thing. Slight differences, but basically the same idea. Okay, so first of all, boundary. What is the boundary of a three-dimensional solid? Well, as you know, all boundaries are kind of the one way to think of it is it's the border between the set and not the set. A nice, easy way to think about it. But we need to interpret boundary now as an oriented idea, right? And so what's the orientation that we take? And the answer is whatever point you're looking at on the boundary, the orientation is, now you're going to be tempted to call that outward. Very tempting to call it outward. And on the outside part of the boundary, it is outward. But more generally and more precisely, what it always is away from where the solid is. So that's the idea. Now, in particular, the solid, for example, is like this, right? And notice at this point, right on the boundary, that's the side of the boundary that the solid is on. My orientation is away from where the solid is. And likewise over here at this point on this solid, what I have highlighted in green, that's where the solid is, and the orientation is away from that solid. Okay, so that's the rule, and yes, in cases when you're looking at points that are on the what you might call the outside part of the boundary, yes, that does mean outward, but that's a special case. Okay, accumulating quantities. We've talked about this. Quick reminder. Every integral we've ever done is an attempt to compute an accumulating quantity, right? That accumulation just means the whole is the sum of the parts. And so anything you compute with an integral, anything you compute the whole of as the sum of the parts, which is what integrals are, right, must be an accumulating quantity. So the weird, unexpected seemingly non-physical, surprising accumulating quantity we're going to think about here, boundary flux. Boundary flux is an accumulating quantity, and just to be a little bit more precise, I'm going to point out boundary flux accumulates over solids in particular. Namely, if you have a solid three-dimensional thing, right? Solid three-dimensional lump, you can talk about its boundary flux. You can cut it into pieces and talk about their boundary fluxes. And the whole is the sum of the parts. So in particular, that's what we mean by accumulates over solids. It's the solid that you'll be talking about as a whole and as in parts. Okay. All right. So now why does this work out? Well, it's morally equivalent to what we saw with Green's theorem. When you slice it, you're going to... whoops, wrong color. I wanted to be the highlighter mode here. When you look at the new face that you create, the new kind of boundary, as it were, that you create when you cut this in half. And this is part of the boundary of R1. That wasn't part of the original lump. And it's also part of the boundary of R2. That was not part of the boundary of the original lump. This new boundary, well, as part of the boundary of R1, away from the solid, is that way. So it's oriented in that direction. But as part of the boundary, oh gosh, color choices. As part of the boundary of R2, that same face, as part of the boundary of R2, away from the solid, is that way. And so, yes, while it is true that when you cut this solid into pieces, yeah, you're creating new boundary. Yeah, of course, there's a new face right there, right? It's going to appear twice with opposite orientations. And we've seen before that when you change the orientation, you're just inserting a minus sign. And so these two instances of that face as parts of the boundaries of R1 and R2 will cancel. Right? Exactly what we need. It's again, now morally equivalent to what we saw with Green's theorem. With Green's theorem, it wasn't a face, it was a curve, because we were in two dimensions. It wasn't flux through, it was circulation along. Right? But still, opposite orientations, just opposite in a different sense of opposite. But still opposite. So again, geometrically different, appropriate to the different geometric context, totally analogous. Okay. All righty. Let's see here. Let me move it along here. So now I'm going to be quick about this part here. Like the big punchline is that flux behaves, boundary flux that is, behaves like stuff. And it kind of doesn't feel like it should, because when you talk about boundary flux, it says the word boundary right there, and you compute it on the boundary, and so you think of it as something that happens on the boundary. You think of it as being on the boundary. And that's an illusion. It's a distraction, right? The point about boundary flux is not that you compute it on the boundary. The point about boundary flux in this context is that it is something you do to a solid. You give me a solid, and I can compute the boundary flux. Right? You give me a sub-chunk of solid on the inside, I can compute its boundary flux. Right? And so, because it's an accumulating quantity, if you were, hypothetically, if you were to choose to think of this quantity that we're interested in, this accumulating quantity, yeah, it's called boundary flux, let's set that aside for the moment. If you just think of the quantity in question as being associated to the solid, and, well, the whole is the sum of the parts, you can just think of it as being in the interior, and however much you get for each piece is how much of that stuff is in that piece. That's how you would do it if it actually were stuff. And if you think of it in that way, if you think of it as stuff, then nothing goes wrong. Because the whole is the sum of the parts, just like stuff is. So that's what I want to, again, remind you. That's how we want to think about these accumulating quantities. Reminder, let's go back to chapter 6. Here's the little quick, alternate point of view that I gave you all in the fundamental theorem of calculus. Right? And the whole idea of the fundamental theorem of calculus, this take anyway, is that we want to think of it as a computation of change. Here's how much the function changed, right, between that point A and that point B, and we compute that change on the boundary, right, at the endpoints of that interval. That's the boundary for an interval. You compute it on the boundary. But nobody is fooled into thinking that that's where change happens. You can see where the change is happening. It's right. Look how steep it is, right? That's where the change is happening. It's right along in here. Right? So same idea. Again, much easier to buy in this context here where you're talking about change because we can draw the graph and I can see the change happening. And it's only two-dimensional even with the graph drawn. So it's just much easier to relate to here. But this, what we're hopefully totally comfortable with seeing about how accumulating quantity computed on the boundary actually happens in the interior, to the extent that you're comfortable with this, I'm just going to ask that you try to take that same point of view when it comes to boundary flux and every other accumulating quantity we'll be talking about. Okay, so accumulating quantities are stuff. Kind of like how mass is stuff. And therefore, you can talk about stuff per unit size, right? And if you take stuff per unit size and multiply by size, not surprisingly, you get stuff, right? So copying, right? Mimicking that same idea, just like we did with circulation back in chapter 6, developing Green's theorem. We're going to think of flux now, being as it is a stuff. I can talk about stuff per unit size, just like any other stuff. Stuff per unit size times size, again, no surprise, gives you stuff. Yeah? Isn't that cool? All right, so with this in mind, this term, this factor, I guess I'll say, flux per unit volume. In the same way that regular density, we use the word density, likewise here, different kind of stuff, flux instead of mass. We're going to call this flux density. Does everybody buy it so far? So, let's see here. You can compute this. Different ways to go about it. There's a version in the book. There's different other versions, different ways to think about it. It's all good. But frankly, the calculations that go into, where do we get this formula right here? How do we conclude that that's the formula for flux density? It's a certain amount of details, and to be honest, years in the future, right? When you're using the theorem that that you were in the process of developing, and when you're, interpreting, making use out of that calculation, important though it is to establishing, the precise, detailed levels and all that, not what you need to remember. Most important thing to me, my take on this, most important thing to understand about this formula is not the calculation of it, but the interpretation of it. So please make sure to understand this is just a formula that allows you to compute flux per unit volume, aka flux density, stuff per unit size, where the stuff is boundary flux. Okay. Now y'all will recognize that formula, and we've seen that formula before in chapter 3, going way, way back. We called it divergence for no given reason, right? I just asserted with no base for why that this formula shall be known as divergence. and that it's interpreted a certain way, something about the field line, the flow kind of being generally outward, something like that. We didn't have any context at that time to justify why in the world would we interpret this formula that way. We're basically there at this point, and a couple of more notational observations, and then I'll get to that. So divergence is abbreviated as div, so heads up on that. You're going to see that notation sometimes. And del dot, you'll remember from chapter 3 as well. So what interpretation do we take? And you can see this. Let's see here. Let me give myself more space. There we go. You can see this interpretation. I'm claiming down here that divergence is how much flux per unit volume, how much of the outward flux is actually happening in a given point. Well, flux, of course, flux is an outward flow, right? Boundary flux happening on the boundary. Boundaries are oriented outward. So boundary flux is a measure of whatever this fluid is, to what extent is that fluid flowing outward out of your set. And this says we're looking at how much of that per unit volume is happening wherever you might be looking. And so I think this interpretation follows pretty reasonably. Then this idea of interpreting divergence as to what extent, in a general vicinity, to what extent is there kind of more of an outward flow than an inward flow, kind of a natural interpretation from this formula here. Okay. All right. Couple of just a quick FYIs. In my physics major way back when, I almost never saw div written as div. I almost always saw it written as del dot. So heads up, you're totally going to see that. That's extremely common. Also, in my physics classes, right, not my math classes, but in my physics classes, which, again, as mostly engineers, y'all are probably mostly going to experience something most like my physics classes. I almost never heard the term divergence. Right? In my undergraduate physics classes, this was the term I heard: flux density. Much more common, at least in that time and place. So this business about a density, this idea of taking a non-physical accumulating quantity per unit volume and calling that a density, not my idea. I didn't make that up. This predates me by a long, long time. Very natural, though. I love the choice. So, in fact, the prevalence of this term flux density is what made me start, decide that it would be a good idea to start pushing terms like circulation density and change density, because it makes just as much sense as this does. Less common, but nevertheless, it makes just as much sense as this does. Okay. All right. Alrighty. So, now let's make a quick interpretation with all this in mind. So again, flux is a kind of a stuff. The question here is about the flux that a given vector field creates through a given surface. We have a ball of radius 6. Boundary flux, I should say. So that vector field creates a certain amount of flux. Doesn't even matter. We don't need to know how much flux that is. It does create a certain amount of a flux. Okay, fine. Of that flux, does more of it come from here, or does more of it come from here? And now again, look, you're going to be naturally tempted to say, well, that doesn't make any sense. The flux, boundary flux happens on the boundary, and neither of these points is on the boundary. And that's a reasonable complaint. Let me remind you, we have, again, this point of view about change. And we can compute a total change. And I could reasonably ask, well, okay, this change that we measure on the boundary, is more of it coming from here, or is more of it coming from here? There's no confusion about that question. There's obviously plenty of change happening here, and there's no change happening here. Right? So in that same sense, I asked the question that we were looking at a second ago. Now, how do we answer these questions? Well, when you're talking about change and you want to know of a couple of points, 1 and 2, between these 2 points, where is the most change happening? Well, the way you answer that question is by looking at change density, aka the derivative. So you compute that, you plug in your 2 points, and the question was about where is more happening. And, well, apparently more is happening at the point x equals 2, because 4 is more. Right? So the density tells you where more of the stuff is. I think that is a very natural take. And so we're going to answer this question here the exact same way. If you're interested in where the flux is coming from, look at the flux density. Right? So we compute the divergence. Now there's some partial derivatives to take the appropriate partials. Here's your formula, right? And so, all right, well, that's what the flux density is, and I can plug in these 2 points that I was given, 4, 0, 0, and 0, 3, 4. Just plug those in, see what you get. And you want to know where more of that is coming from? Well, more of that, apparently, is coming from this point B, because 75 is more than 48. Is that cool? All right. So this was a the purpose of this example here is to underscore the geometric interpretation of divergence as being flux density, as being where the flux is coming from, etc. So now back to developing the theorem. We have all the pieces. We just have to snap them together at this point like Legos. We have this quantity called boundary flux. You can think of it as a formula, but I want to think of it as a quantity, computed by a formula, but a quantity. The key point, the thing that makes it all work, is that this is an accumulating quantity. Right? We talked about that new face and the opposite orientations. It's an accumulating quantity, whole of the sum of the parts, which of course is exactly what this says. And when you have an accumulating quantity, it being a kind of a stuff, you can talk about its associated density. So rewriting d phi here as divergence times dv is just really the interpretation of, divergence is flux density. So all that we've written down on this screen here right now is just, again, putting together the pieces that we've already established. And check it out. We have ourselves a new theorem now. And if you find yourself interested in computing a flux, you can compute that. Well, we got to check the conditions, but the hope here is that we can compute that flux with this triple integral, where the integrand is divergence. Okay, how are we doing? Let me. I'll inhale. Give you all a chance to squeeze a question in. If you might have one. Anybody have any questions? Example coming, of course. Okay. All right. So let's do it. Let's see here before I get into the details here. So here's our surface that we're going to be interested in. We're going to be interested in a flux. You can see right here at the bottom we're looking for a flux through this surface S, S being the inward-oriented unit sphere, perfectly reasonable surface. Want to compute the flux through that inward-oriented unit sphere. How are we going to do that? Well, it's a flux. The theorem that we just developed is a theorem about flux, and naturally we would like to use this theorem. Very importantly, though, we have to think about the conditions, and are the conditions of the theorem satisfied? In particular, notice this is not just any old random flux off the street. This is a special flux This is a boundary flux. Has to be a boundary. This is not a minor point. This is essential to the statement of this theorem. Gauss's divergence theorem will only address boundary fluxes. Now, again, this is not a, one of these kind of fussy kind of regularity sort of conditions. This is a huge, huge deal. The entire argument that we made rests on fundamental assumptions that in particular it's boundary flux that we're computing it. That's what makes it accumulate. And if you take away it being a boundary, then there is not only is there no theorem, there's no argument, right? Another take, if you might prefer, this thing has to be a boundary because the thing that it is a boundary of is going to be the domain for our new triple integral. So very importantly, and you'll remember I made an almost identical statement when we were talking about Green's theorem. If it's not a boundary, then there's nothing for it to be the boundary of. So there is no domain for your new integral on the right-hand side. So it's not that, these two integrals aren't necessarily equal if it's not a boundary. No, it's that there is no integral for this to be equal to. Right? So just tremendously important. And if you, the reason I'm making a big deal out of this is because I tragically do see the following happen. Oh gosh, too often. Right? Any is too often, I guess, but disappointingly often, that students will take a non-boundary flux and start writing down triple integrals. And very importantly, there is no such triple integral. Nothing that follows even exists and just doesn't make sense at all. So be very, very careful about this. Only apply the divergence theorem to fluxes through boundaries. Okay, now with that emphasized, let's ask the question then. Is our surface a boundary? Unit sphere. Here's the unit sphere, inward oriented, as I have drawn here. And now this surface S, this sphere oriented inward, is that the boundary of everything? And tragically, no, it's just not. It's oriented all wrong. That's not how boundaries work. Right? Boundaries are oriented away from the solid. This surface, at least in relation to this solid, right? This surface is oriented into the solid. Not a boundary, dead in the water. Cannot apply Gauss's divergence theorem. Does that make sense to everybody? Okay. All right. Now, of course, the hack fix, you can probably see this coming, is to notice that, that's not a boundary. But if I look at the very similar surface here that I'm calling S minus, right? Same surface oriented the opposite direction, S minus. Well, this is a sphere oriented outward that is a boundary. It's literally the boundary of this ball B, and we're in business. Right? So all you have to do when you find yourself in this situation and you're looking for flux through something that's not a boundary is just entertain the possibility that if the orientation was the issue, just recognize that with a minus sign like I've done here. And now the integral that remains, here is an integral over S minus, which is a boundary. And now, well, like I say, now we're all good. Does that make sense to everybody? Okay, and of course, now once you have a boundary, reminder, boundary flux, then Gauss's divergence theorem says because that's a boundary, I can rewrite that boundary flux as a triple integral of divergence, and we'll write that down next. And again, here it is. That boundary flux, triple integral of divergence. Now, of course, that minus sign comes along for the ride, right? So don't forget that minus sign. It's not just a cosmetic, thing here. It sticks with our work as we proceed. How we doing? Everybody all right? So here's what I think would be a really nice exercise. Again, one of the most important things to me that y'all take away on stuff like this is the analogy, right? So the very first example that we did when we wrote down Green's theorem was really, really similar to this, in the sense that we had a thing, but it was oriented the wrong way, and we did the minus sign trick, and then it all of a sudden was a boundary, and then we cited, well, of course, that was chapter 6. I'm talking about circulation, and we used Green's theorem. So same story here, flux instead of circulation, divergence theorem. All right, it's all over but the shouting. There is one little cool little bit that I think needs to be noted, and that is when you compute the divergence here, the divergence ends up being this. By the way, make sure you can do that. Remember what the formula is for computing divergence of the vector field. Here's your vector field. Make sure you can compute, for example, the divergence of that vector field, and make sure that you get this right answer, 3 plus x. Having done that, let's ask how would I compute that integral. My domain is this ball, solid ball. You might be thinking spherical coordinates, and you could do that, right? It's going to be a certain amount of effort. A bunch of trig gets involved, as we all recall from spherical coordinates. The slick move, I think, is to notice that you can break up this integral into two separate integrals. And even though this integral over here, the integrand's not constant, and it's not symmetric, and it's not anything nice particularly, I guess it's at least a polynomial, that's worth something. But it's not constant, it's not symmetric. But when you break it up into pieces, right, the first piece is constant, and the second piece is symmetric, right? So this is a lovely little, an easy, right? Easy little trick, and always be on the lookout for this little move where you take an integrand and separate it into chunks, and those chunks might be collectively much easier to deal with individually instead of as a whole. All right, how we doing? You might say difficulty is not an accumulating quantity, just to bring it back. Right? Okay. All right. Okay, so let's do some physics. A couple of physical examples. It turns out that the divergence theorem has lots of important and powerful applications, you might say. I like to think of them as manifestations in the physical world. It's kind of funny how this works out, but a lot of aspects of the physical world are just straight up it's like we wanted to build a model of what divergence and the divergence theorem look like, and thankfully the physical world that we live in just happened to be put together that way. It's wonderfully fortunate. So here's my favorite starter example, and that is a light bulb. So let's imagine we have a little LED light bulb right there. LEDs, of course, are teeny tiny. They're not geometric points, right? But they are teeny tiny. So teeny tiny little light source. And of course, what does a LED light bulb do? Well, it produces and emits light particles called photons. Right? Is that cool? All right, so here's what the flow of those photons looks like. It's kind of outward like that. Now, you'll notice that the arrow that I've drawn further out is shorter. And the further you go out, the shorter these arrows get, which seems confusing because, wait a minute, I thought light always moved at the speed of light, right? So why are the field lines getting shorter? And the reason why is because in this instance, when I say it's flowing like a fluid, remember we have two different ways that we can use vector fields to represent fluid flows. One is for the field vector to be the velocity. That's not what we're doing here. the other way that we can use a vector field to represent a fluid flow is density times velocity. And so that's why the field line is actually shorter here. It's not about velocity. It's, of course, the velocity of the photon is always the same. What's going on here is that when you're looking near where the light source is, there's a lot of photons really close together. And as they get farther away from the light source, they also get farther away from each other. And the density decreases. Photon density is a lot lower out here, and it's a lot higher over here. Does that make sense to everybody? So that's why these field lines are shorter. And we're going to talk on the next page about what the actual formula is for that vector field representing this fluid flow, this fluid of photons. Kind of a weird fluid, right? But again, behaves like a fluid. Okay, so let's talk about flux. And a reasonable question we could ask is, what is the flux through, let's say, this sphere? I just make up some sphere, doesn't matter. Well, there's going to be a bunch of flux, right? Now, why is there going to be a bunch of flux? Well, you can just look at the arrows, right? You can see the arrows are going perpendicular to the surface, and y'all remember how flux is computed. But here's another way to think about it, I think a physically satisfying point of view. If you have a light source at the middle, and it's shooting out photons, well, those photons have to get out, right? And that's what flux computes, right? Independent of the geometry of the vectors, I mean, just thinking about the stuff of it all, there's this fluid of photons, and they will be leaving that purple sphere. They will be passing through that purple sphere. And so there is going to be some sort of a quantity per unit time of photons flowing through that surface. Does that make sense to everybody? You can do that geometrically or just physically. Okay. All right, so we've got a flux. Now, y'all recall, I like to come down here to the fundamental theorem of calculus point of view, and because again it's so relatable, and we've got, in this context, change that we measure on the boundary, but of course it's happening in the interior. The derivative points right to where it is happening, right? And so even though it's computed on the boundary, it's happening in the interior. Well, I'm going to ask the same question now about this situation. We've got all this flux that we're seeing on the boundary. We've got all these, flow rate of photons. I've got, a bunch of photons per unit time passing through that surface. Where are they coming from? Right? Where are these photons coming? We're detecting these photons passing through the surface of the sphere. Is that where they're coming from? Of course not. There's no photons coming from here. They show up here because that's where I happen to be looking, but that's my deal. That's not where the photons came from. Photons come from the photon generator, comes from the LED, comes from the light source. So I claim, and this is a calculation y'all can do on your own if you're interested in doing so, but you don't have to. If you're looking at points away from where the light bulb is, doesn't apply to the light bulb itself, but just anywhere away from where the light bulb is, if you compute the divergence, you will get 0. And this is divergence doing its job. This is divergence saying, okay, divergence, all right, I detect where flux comes from, and there's no flux coming from here because there's no light that's being generated here. There's no light being generated there or there or there or there. That's not where the light's generated. Where the light's generated is, again, the light bulb right there. Right? And this will show up by the divergence. And if you were to write down, and things get a little weird when you try to write down what this vector field actually is, near where the LED is, a little strange. But if you were to compute that divergence, you would get a very large number where the light bulb actually is. That's pointing to that being where the light is coming from. You measure how much light it's creating by the flux through this boundary, but it's coming from the interior. You buy it? So again, I'm a big believer. Now, I push this point of view a lot that, I know it's detected on the boundary, but it's actually happening in the interior. And this is my best shot at a physical example that just really makes that go down easy, I hope. So anyway, it's a nice little metaphor. All right, moving along. Different physical example next. This one's a totally different kind of a fluid. There are different kinds of fluids. Not in a chemistry sense, but in terms of how they behave. So in particular, here we're going to talk about a physical fluid. Let's talk about a gas, right? Imagine that we're out in, somewhere in outer space somewhere, and there's a gas cloud, right? And there's a certain amount of gas that's just kind of sitting in there, just not doing anything. The gas is just sitting there. Okay. Now imagine that the temperature of that gas starts rising. I don't know how much y'all have seen in physics classes, but when temperature goes up, then the gas will expand. Okay, so that's the scenario I want to visualize. The field that I've drawn here is a picture of how the gas would, if the gas were sort of expanding, this is what the flow field would look like. The idea being that, wherever you might happen to be, you're going to be flowing outward, right? Except, I suppose, look, if you're at the center of that gas cloud, if you're at the center, then as the gas expands, in some sense, the center doesn't move. So there's no motion of gas right at the center. There's lots of motion of the gas if you're out near the edge. In between, it's going to be kind of in between. And altogether, and I'm just going to assert this, I think this is pretty believable, but I just assert that the flow is going to be proportional to the position vector. That's that outward, kind of radial outward vector field that I have drawn there. Okay, I'm just going to claim. Okay, now, if that's the case, then I make a simple physical appeal. If your gas is expanding, if the gas is all flowing outward, then the density is going to go down. Right? Same amount of gas. We're not creating any new gas. Grand total, though, all that same gas gets distributed over more space, and so the density is decreasing. Okay. All right. So let's talk about flux then. And again, we're going to think about flux through some sphere well inside of the gas cloud. Right? And of course, there will be some flux because, after all, our flow is outward. And what is this flux computing? Well, it's computing how much gas per unit time, quantity per unit time of gas flowing out of our little imaginary purple sphere. Right? So how much gas is leaving from the inside, from this ball? All right, so let's write this down. The amount of mass of the fluid that's leaving your solid interior. Okay, now writing down the divergence theorem. There it is, the divergence theorem. And by the way, you can totally compute divergence, keeping in mind that your vector field, we have an explicit formula for it, and you punch up what the divergence is. It ends up being 3K. By the way, make sure you can do this. Make sure you can get this 3K as the divergence of this vector field. Now, how are you going to do that? The trick here is to notice that the formula I have written down for the vector field is in vector form, not coordinate form. all you got to do is write it in coordinate form. And, of course, we have this handy-dandy formula for divergence. Once you have your vector field in coordinate form, that's your formula. Okay, so make sure you fill in those blanks. Make sure you're good with that. Where was I? Here we go. Okay. So, let's see here. So let's, putting it all together again. We're thinking about flux through that surface. The flux is clearly telling us how much mass per unit time we're losing out of that surface. What does this 3K represent? Right, physically? Well, physically, that's divergence. Divergence is flux per unit volume. The flux was quantity per unit time of fluid that we're losing. So quantity per unit time per unit volume. Quantity per unit time per unit volume. Now let me say the same thing, shuffling the words around a little bit. That's quantity per unit volume per unit time, or density per unit time. So that's the interpretation that we take away here, and that is that divergence is telling you the rate anywhere in the middle here, anywhere in sort of inside here, how fast is that density decreasing? And of course, we started this example with the observation that, well, of course the density is decreasing. We have a certain amount of gas, and it's taking up more and more space. If it's taking up more and more space, it's more and more sparse, or less and less dense. So divergence, in this context, tells you the rate of decrease of density. That's just another kind of it's a different physical manifestation of the divergence theorem, but I think also a really good one. And again, also really natural. Right? There's nothing abstract or spooky going on here, right? It's just gases and flow and stuff like that. Okay. Now, let me emphasize the reason that we get these different interpretations in these two examples, the photon example versus the gas fluid flow example, is because these are fundamentally different kinds of fluids. And that's just the nature of life, is that there are different kinds of things sometimes. So, in particular, notice when you're talking about photons, you are literally making photons. That's what light bulbs do. They're sitting there pumping out photons. You're creating fluid. Not happening here. Right, in this example down here, we're talking about a fixed amount of gas. There's only so much gas. And it's moving, but we're not creating any. Right? Also different, while we're on this topic, I'll point out, when you're talking about the photons, photon density never changes as long as your light bulb doesn't move. Right? Think about that light bulb right there. Think about how many photons there are sort of in this general vicinity right here. We're not collecting photons there. The photons flow in, flow right out. Right? So the density is constant when you're talking about the photons. Not here, not when you're talking about the gas. When you're talking about the gas, the density of the fluid is literally changing. Right? So these are fundamentally, physically different fluids, and so that's why we get different physical interpretations of divergence. But I think it's really healthy to be aware of both of these, and so that you know how to make interpretations appropriate to your context. And just while we're here, I'm going to point out that it gets weirder than this. In fact, there are some kinds of fluids where both the fluid is being generated and the density is changing too. In other words, in some sense, the complexities of both of those examples can come up in sort of a combined way in other kinds of fluids. And that can be dealt with, and the divergence and the flux can be interpreted in terms of whatever else you might know about the fluids. It's a road that we don't have time to go down, but we have all the tools. If we wanted to, we just don't have time. So anyway. Okay, last thing I want to talk about. Oh, let's see. No, what are we doing on time? We have 15 seconds left. So happy weekend, y'all. We'll draw the line right here and pick up on Monday. Have a good weekend. See you later.